Hello, and welcome to your video on how to find the support reactions for an axially loaded member that is statically indeterminate. Now, before you even continue watching this video, make sure you have the handout that goes with this video that's available to you on Camino and follow along. These same images are there and you can draw right on your handout. So, what we see is that our axially loaded member is fixed both at A and at C, but there is a force P applied at point B, 3/5 of the way down from A. So I've started the free body diagram, and because we are statically indeterminate, or because we have supports at A and C, we're going to end up with a force at A and C, and then we'd still have our load P at B. Because this is axially loaded, and there's no horizontal or moments applied, horizontal forces, we can just immediately say that any shearing or moments are zero and we only have normal forces. So when we go to do our statics on this problem, obviously summing forces in the x and summing moments give us zero, and so all we're left with is to sum forces in the y. So we have force at A plus force at C minus P equals 0, and we have one equation and two unknowns. So that leaves us trying to look for another way to get another equation, and we want to again turn to the deformation. So from the deformation, we're going to look at two different methods. The first is the redundant force method, and we're going to apply that. And then we're also going to just directly apply kinematics to the fixed axially loaded member. And remember, kinematics is just the geometry of the deformation. So let's look at method one, the redundant force method. We know that the redundant force method, we're going to rely on our good friend superposition. As a quick reminder of superposition, that literally is just when you have a member that's still behaving linearly elastically. It could be a beam, a column. You load it with multiple loads. Well, it's much easier to take apart the different loads and analyze those individually and then sum your results back up. And those results can be deformation, stress, internal shear moment, support reactions, whatever, as long as you stay linearly elastic. So if we wanted to apply that to our particular case, well, with the redundant force method, and you can see a long description of this on your handout, so there's lots of words for you as well to go back and read later, but we need to remove a redundant support. And now you get to choose. We could remove the support at C and just have support at A. Or we could say, no, I want to remove the support at A and just have the support at C. The key thing is those two supports must match. You cannot on the first column have the support at C and then on the second column have the support at A. The two columns that you draw, their supports must match. That's critical. Now, what we want to look at is we want to then put the support reaction that would have been at A on our second column. And we also want to go ahead just for now and sketch what sort of deformations we might see from the two loads. So in our first case where we have our existing force P, there's no load between A and B. So all the deformation that you see at A is just the deformation between B and C, and then point A just drops down the same amount, the deformation from B to C. Whereas on our second column, the stretching occurs between A and C, so our deformation at A is the deformation from A to C, right? So this is the behavior that's happening, and a couple things that would be good to note is that now both members are determinate, and that's what the redundant force method does for us. We remove the redundant support and we replace it with a force that represents the redundant support, and that's what that force at A was. That's our redundant support reaction. And so if this truly matches our original beam, if case 2 matches originally case 1, which is the original beam, it only works if, and I want you to think about, what is the deformation compatibility condition, and try to write that down. hopefully what you noticed is that point A really shouldn't be able to move in our original beam. So the deformation from A1 plus the deformation A2 has to equal to 0, where deformation is just our friend play, PL over AE. So that means we would have minus P times that distance from B to C, 2L over 5, and over AE, plus then the force at A, which acts over the entire length L, also over AE. All that's equal to 0. Since that's equal to 0, we can divide out the AE, and we can also divide out the L's. And so what we end up with is that the force at A is just 2P over 5, which then from statics, we can say the force at B, that should be the force at C. So let's get that right. Let's make that the force at C would be 3P over 5. All right, so that is the redundant force method. Again, just take out the redundant support, but replace it with an equivalent force and superimpose the behaviors while enforcing compatibility. Now, our second method is just straight using kinematics. When we're using kinematics, we actually will keep the redundant support and attempt to solve the indeterminate problem just by looking at it. And so the first thing we want to do is look at the geometry of the deformation, or the deformation geometry, and we know, because it's fixed at A and it's fixed at C, that the overall deformation between A and C has to sum to 0. But we can't write one PL over AE expression from A to C because we don't have constant load from A to C. Remember, PL over AE assumes P, A, and E are constant in that length L, and our P is not constant from A to C. Now, to see that we can add A to B plus B to C, we can actually look at another little small aside, and we talked about this a little bit in the first method, but if you look at our first loading, if we just assumed we had load at B, we'd have the distance from A to B, and once the load was applied, we would only see compression occurring between B and C. Let's assume C is fixed and it can't move anywhere. B would move down to B prime, so A just comes along for the ride, but the distance that A moves down is still just the deformation from B to C, and the distance between A and B, or A and B prime, it's the same. It hasn't changed. Versus if you have a member that just has an axial load along the whole length, then the whole thing's going to stretch, and your new length would be the original length plus the deformation along the entire length. Well, in our case, we have both of those happening, so we have to figure out a way to combine them. And again, we have to say, okay, our load changes between A and B and C, so that's where we're going to make our addition, and we'll say the deformation from A to B plus B to C has to equal 0. So now, if we just write that out using PL over AE, we'd have the force from A to B plus the length from A to B over AE plus the force from B to C times the length from B to C over AE. So we need to get the forces in those two sections. An axial diagram is going to be our friend in this. And so we can actually draw, if we start at A, because things are in tension at A, that would be positive. So we'd have a positive FA that goes from A to B. But at B, we end up dropping down and subtracting out the force P because that's in the opposite direction, constant until we're back up to C. And so we're going to go back up to 0 at C. And so that means between A and B, force AB, then by our plot is just FA, and force BC is going to be FA minus P. So we can actually now go back to our equation and put those values in. So we'd have FA times the length AB, which is 3L over 5, plus FBC, which is actually the quantity FA minus P, times our length BC, which is 2L over 5. And we can cross out the AE since it's all equal to 0, and we can even cross out the L's. And so we just end up with 3/5 of FA is plus 2FA over 5 minus 2P over 5 equals 0, and FA equals 2/5 P. So of course, F sub C is equal to 3/5 P, just like using the redundant force method. So either method works, and in most cases, the choice is up to you. Sometimes one method is better than another for particular loading, but you learn that from experience. Thanks for watching.